Anatomy 32, Chapter 21, Special Senses. Topic, Static and Dynamic Equilibrium. So, equilibrium is another special sensation that we possess. You might not have been aware of that, but it turns out it exists and we have it. And the mechanisms for equilibrium are found in the internal ear, specifically in the structures of what's called the vestibular apparatus. And the vestibular apparatus is composed of the saccule, the utricle, and the semicircular ducts. And this is where we find the receptors for both static equilibrium and dynamic equilibrium. So we'll start with static equilibrium. Static equilibrium is the position of the body relative to gravity. However, since it's localized to the head, it's really more the position of the head relative to gravity, so that if you move your head so that you're looking down or looking up or laying your head on the side of your shoulder, static equilibrium will be able to let your brain know how the head is positioned. And the receptors are localized to the utricle and the saccula found in the vestibule of the bony labyrinth. So when you look inside the utricle or the saccula, you will find an area called the macula. The macula. The macula is a thickened region where the cells themselves are bigger and where you'll find the associated hair cells, which are the sensory receptors. And the macula has on its surface a structure called the otolithic membrane. The otolithic membrane is a gelatinous mass that contains otoliths, which are just calcium carbonate crystals. And the way this works is you have the hair cells themselves surrounded and held in place by support cells, which are types of epithelial cells, and the hair bundles of the hair cells are embedded in the otolithic membrane. Then, when you change the position of your head, gravity will pull on the otolithic membrane, and as it pulls on the otolithic membrane, it will ooze or move in that direction. And as the otolithic membrane oozes in that direction, it will bend the hair bundles, and that will be the stimulus, the signal that the hair cells transmits to the sensory neurons. So again, hair bundles embedded in the otolithic membrane attached to the hair cells that synapse with the sensory neurons. And that means, of course, that hair cells are mechanoreceptors. Mechanoreceptors because their physical shape is changed. And that is the stimulus. That is the signal. All right. Then there's also dynamic equilibrium. Dynamic equilibrium is the body position in relation to sudden movements or rotational acceleration. So when you turn your head really quickly, or say you're driving and you make a sharp turn, that sensation you can feel, that is dynamic equilibrium. And little kids love dynamic equilibrium because they can overwhelm it by spinning in a circle really, really fast and getting dizzy. So the structures important for dynamic equilibrium are the semicircular ducts and, of course, the ampulla of the semicircular ducts. So as we know, there are three semicircular ducts. They are lying in basic orientation for the three dimensions: up, down, out, right, left, and forward, back. And then within the ampulla, the widened area of the semicircular ducts, we have this area referred to as the crista, which is a small elevation within the ampulla composed of support cells and hair cells. And then there's this cartilaginous structure called the cupula, so that the hair bundles of the hair cells are embedded in the cupula, this gelatinous cartilaginous mass. And then when we turn our head in a direction, or our body gets moved in a direction, that will cause a current in the fluid within the semicircular canal, and that fluid would then hit the cupula, causing it to bend, which then causes the hair bundles of the hair cells to bend, and that would be then the signal that gets transmitted to the sensory neurons, making the hair cells, of course, mechanoreceptors, because the sensation, the signal is the bending of the hair bundles of the hair cells, a physical change in the receptor's shape. All right, the equilibrium neural pathway is a little more complicated than some of the others, but we're going to keep it simple and ignore some of that complication. So basically, the equilibrium signals travel via the vestibular branch and enter the vestibulocochlear nerve. So the first order sensory neurons are traveling through the vestibulocochlear nerve and then reach the brain stem, either the pons or the medulla oblongata. They then synapse with second order sensory neurons, and at least some of those will then go up to the thalamus, where they will synapse with the third order sensory neurons and lead to the vestibular area in the temporal lobe. But as you can see, equilibrium, that sensation, is important to a lot of other structures, and so it's going to go to the cerebellum and do some other stuff that we're not going to worry about. We're just going to talk about how it goes via first order through the vestibulocochlear nerve to the brainstem, second order to the thalamus, third order to the vestibular area in the temporal lobe. And that is it for this chapter 21.